So can you see my slide?
Yes,
Yes,
sir.
sir.
Okay. Again, what happened? So first I shall explain again this flat band voltage. This flat band voltage refers to the applied gate voltage for which there is no band bending in the semiconductor. And consequently, you will not have see any space charge in the semiconductor region. And here you see the band diagram. On the left hand side, it is the metal side. And the Fermi level has been lifted by some amount, because this flat band voltage is usually negative. So negative into minus q means there will be a shift in the upward direction. So now in the middle there is a tilt in the band diagram, conduction band of this oxide. This is the actually insulator, for example, say silicon dioxide. And on the right hand side, you will have this flat band condition, means all the horizontal lines, means EC. The semiconductor oxide interface, there is no band bending. That means flat. It is horizontal conduction bandage. Then if you go down by an amount of Eg, you will find this horizontal valence band, top of the valence band. This is horizontal line. And again EFI, this dashed line, intrinsic Fermi level, it is also horizontal. And you will see the Fermi level EF. So this actually band diagram refers to the flat band condition. And we'll now show some calculations of this gate voltage. I discussed this earlier also, but there was some mathematical step jump, but here all the steps are available in my notes. So here this dashed flat band, actually these oxide charges, in this trap charges is in general positive charges. And this condition, so can anyone explain why we need to apply some gate voltage to make the bands in the semiconductor flat? Here. So if we do not apply any voltage across this MOS structure, our intuition is that the bands will be flat, but it is not the case. We need to apply some negative voltage at the gate terminal to make the semiconductor bands flat. Why is it so? Can anyone explain or guess? D. Chakraborty, can you guess?
যদি ভোল্টেজ অ্যাপ্লাই না করি মানে
তাহলে ব্যান্ডটা ফ্ল্যাট থাকে না। ইউ নিড টু অ্যাপ্লাই সাম নেগেটিভ ভোল্টেজ at the gate terminal to make the bands flat. Why is it so?
স্যার ওয়ার্ক ফাংশন মেটাল আর সেমিকন্ডাক্টরের জন্য তো সেম না, সেই জন্য কি?
এটা একটা রিজন, রাইট?
আচ্ছা, ট্র্যাপ চার্জেস,
রাইট। So there are two important causes, means reasons why the bands in the semiconductors are not flat when we have not applied any voltage across it. So it is the main two reason. There is some difference in the metal semiconductor work function, and there must be some trap charges in the oxide. So mainly these are two reasons which actually together make the bending of the band at the oxide semiconductor interface. So to make the bands flat, we need to apply in general some negative voltage to the gate terminal. So here it is written in my notes also. So there will be some trap charges. In general, it is some kind of positive charges inside the insulator. And the positive charges has been identified with the broken or dangling covalent silicon bonds near the oxide semiconductor interface. So now we can, for the purpose of analysis or simplify our analysis, we assume that an equivalent trap charge per unit area, it is denoted by Q dashed SS, located in the oxide, just at the oxide semiconductor interface. Dashed means it is the charge per unit area. Dashed indicates the charge per unit area. So these parameter, uh, uh, if we apply zero gate voltage, then zero gate voltage means the voltage drop across the oxide with no bias plus surface potential with no bias, it must be equal to minus of metal semiconductor work function difference. So if we apply some amount of gate voltage, that is Vg, that will be distributed to develop voltages across the oxide, then surface potential, and the metal semiconductor work function. This equation I have already discussed in my last class. So Vg, you must remember it is equal to Vox. Vox is the oxide semiconductor voltage drop across oxide, and phi s is the surface potential, and phi ms is the metal semiconductor work function difference. So when we attain this flat band condition, what would be the charge distribution within this structure? First, you come on the left hand side. This is the metal. There will be some charges Q dash m, means the gate charge per unit area, and there will be some equivalent oxide charge per unit area, that is denoted by Q dash SS. And due to the flat band condition, there will not be any charge in the oxide. So therefore, if we consider the charge neutrality condition, the sum of these charges must be equal to 0. So therefore, we can relate this Q dash m. That means it is the equation Q dash m plus Q dash SS equal to 0. I already told you that usually the oxide trap charges, this is positive in nature. Therefore, we must need some negative charge on the gate terminal, so that the sum total algebraic sum of these two charges will be equal to 0. So therefore, we need to apply some negative gate voltage so as to make the bands flat in the semiconductor. So I think it is clear. So now we can relate Q dash. Is it clear, Indrajit?
Yes, sir, clear.
Okay. So now we can relate Q dash M to the voltage across the oxide. This is the VOX is the voltage drop across the oxide gate insulator. That is equal to Q dash M by COX. COX is again, it is the oxide capacitance per unit area. you know that Q equal to CV, simple formula. So therefore VOX, it is equal to Q dash M by COX. So therefore, if we combine, if we substitute this value in equation 7, then you will get VOX equal to minus Q dash SS by COX. Just to put Q dash M, that is equal to minus Q dash SS. So you will get this VOX equal to minus Q dash SS by COX. So in the flat band condition, the surface potential is 0. That is why phi s equal to 0. And Vg will be equal to flat band voltage, that is VFB, and that is equal to phi ms minus Q dash SS by Q by COX. So equation 10 is very important because you will maybe asked to voltage depends on the metal semiconductor work function difference and the equivalent oxide charge density, Q dash SS, and also on the oxide capacitance per unit area. So here you see some problem. This calculate the flat band voltage for an MOS capacitor with a P-type semiconductor substrate. Consider an MOS structure with a P-type semiconductor substrate drop to Na. It is the acceptor concentration, that is equal to 10 to the power 16 per cc. A silicon dioxide insulator with a thickness of T oxide equal to 500 angstrom, means 50 nanometer, and an N plus polysilicon gate. Assume that Q dash SS equal to 10 to the power 11 electronic charges, means electrons per unit area, means per square centimeter. So it is the formula for work function difference. This is phi ms equal to minus of band gap of the semiconductor Eg divided by twice into electronic charge Q plus phi fp. So it is equal to, you know, the band gap of silicon, how much? 1.11 electron volt. So just half of the band gap means 0.55 volt. Because it is Eg is given in electron volt and it is divided by electronic charge, so unit will be in volt. So 0.55 volt plus 0.26, it is actually kT by Q ln. 10 to the power 16 is the acceptor concentration divided by the intrinsic silicon concentration, that is equal to 1.5 into 10 to the power 10. So if you work out this numerical, this natural logarithm, you can find it, it will be equal to minus 1.1 volt. So is it clear, this expression? Shobik, is it clear?
Yes, sir.
Okay. Now, next step is to find the oxide capacitance, COX. You know that the capacitance means epsilon A by D. Epsilon is the permittivity of the dielectric, A is the area, and thickness is the TOX. Here we are considering unit capacitance per unit area. Therefore, A is equal to 1. So therefore, epsilon OX by TOX. So what is the value of the permittivity of oxide, silicon dioxide? It is 3.9 into, this is the permittivity of vacuum, 8.85 into 10 to the power minus 14 divided by oxide thickness in centimeter unit. So ultimately we will find 6.9 into 10 to the power minus 8 farad per square centimeter. So now equivalent oxide surface charge density Q dash SS, you know the per unit square centimeter per square centimeter the electrons are available 10 to the power, the number of electrons is 10 to the power 11. 10 to the power 11 into electronic charge means 1.6 into 10 to the power minus 19 coulomb. So it is equal to 1.6 into 10 to the power minus 8 coulomb per centimeter square. So now you apply this relationship to find the flat band voltage, that is VFB equal to phi ms minus Q dash SS by COX. So first term is equal to minus 1.1 and the second term is you are just putting the value of Q dash SS and then the COX. So it comes around minus 1.33 volt. It is the value of the flat band voltage. So flat band voltage is found to be negative. So most important thing is that you must take care of these units of different quantities. Otherwise, you may actually calculate some absurd value of this flat band voltage. So in some, I have seen the answer script of many students. They actually do some usual mistake regarding units. So if you actually do not convert to the appropriate unit of different quantities, you may not uh, determine the quantity. This quantity means this parameter flat band voltage correctly. So you must be careful regarding these units of different parameters. So if you have any question regarding flat band voltage, you can ask me. Surajit, is it clear how to determine this flat band voltage?
হ্যাঁ স্যার বুঝতে পেরেছি।
Okay. So now I come to the threshold voltage. Threshold voltage is another very important electrical parameters pertaining to MOSFET. And in case of this bulk type of MOSFET, it is defined as the gate voltage when the surface potential phi s equal to 2 phi fp for n channel MOSFETs and phi s equal to 2 phi fn for p channel MOSFETs. I already discussed the condition of the onset of the strong inversion. Actually, this threshold voltage corresponds to that point, and the threshold voltage will be derived in terms of this electrical and material parameters of the MOS capacitor. So under this flat band, this condition, under this threshold inversion point, the charge distribution within this MOS structure actually looks like this. So when the MOSFET is under threshold inversion point, means it is actually at the onset of the strong inversion. So the charge distribution at different regions will look like this. So Q dash empty, T for threshold inversion point. So Q dash empty means charge on the gate per unit area under this threshold condition, and Q dash SS is the charge in the oxide semiconductor interface, but in the oxide per unit area, and there will be some depletion charge that is per unit area, that is Q dash SD maximum. So actually here XDT is denotes the maximum depletion width. So if we consider unit area, at the interface. So what would be the volume? Volume is uh, x dt into 1. This is the volume. And acceptor concentration Na. So multiply it by Na. So you will get the total number of acceptor impurities, or here you say that all acceptors are ionized, therefore acceptor ions per unit area. And if you multiply it by electronic charge Q, then it will be equal to the total charge, total depletion charge per unit area. So there are actually three charge densities, one at the gate terminal, unit per unit area of the gate terminal, that is denoted by Q dash empty. And the second one is within the oxide per unit area of the oxide. This is basically trap charges or the interface trap charges. And next one is the depletion charge. So here inversion has charge density is very small, so we are neglecting this one at the threshold inversion point. Therefore, so if we actually neglecting this inversion charge density at the threshold inversion point, so we can write from the conservation of charge, that is equal to q dash mt plus q dash ss equal to mod of q dash sd maximum. So these two charges for n-channel charges, n-channel MOSFETs, threshold voltage will be in general positive, and the oxide charge trap charges, it is also positive, but here depletion charge, it is negative because it consists of the ionized acceptors, it is negative. So in equation 10, in equation 11, on the left hand side, it is the total amount of positive charge per unit area on the gate as well as on the oxide, in the oxide. And on the right hand side, it is the depletion charge per unit area. So they must be equal uh, so far as the conservation of charge holds good. So what is the value of this Q dash SS maximum? So it is actually equal to QNA, and the maximum width of the depletion region, that is XDT, means the maximum extent of that depletion width. So it is actually XDT is the width of the maximum width of the depletion region. So is it clear? Equation number 11. Sudeep.
Yes, sir, clear.
So here we have neglected the inversion layer charges because at the threshold inversion point, the inversion charge density is much less. So therefore, we are not taking into account the inversion charge density. So we consider only three charges which are available on the gate, in the oxide interface, and at this channel, within the channel, in the vicinity of the interface. Now it is the well-known equation, that is the gate voltage is equal to Vox, means oxide voltage, surface potential plus metal semiconductor work function difference. So now at threshold, we must set Vg equal to Vth. Vth is the threshold voltage that creates the electron inversion layer charge, and the surface potential will be equal to phi s equal to 2 phi fp for n-channel MOSFETs. So you write here on the left hand side, replace Vg by Vth, oxide voltage Vox T for threshold inversion point, and phi s will be equal to 2 phi fp. and phi ms will remain the same. So under this condition, this is the band bending in the semiconductor. So here you see the all the three bands means EC, EFI, and EV bend, they bend downward at the interface, but EFI will remain the same. It is the Fermi level, and there will be a tilt in the oxide uh, conduction band, and there will be a shift in the uh, actually this is the position of the Fermi level at the metal side, this continuous line. So the voltage VOXT, it is the oxide voltage at the threshold inversion point, that is equal to Q dash MT by COX. VOXT equal to Q dash MT means 1 upon COX uh, mod of Q dash SD maximum minus Q dash SS. So if you substitute these values from equation 11, you can arrive at this equation number 16. So use equation number 11 and 15, you can get this equation number 16. One second. So this equation 16, you can determine the value of oxide voltage at threshold inversion point, and if you use this equation to find the threshold voltage, this threshold voltage VTH can be given by this Q dash SD maximum by COX minus Q dash SS by COX plus phi ms plus twice phi FP. So you need not remember all these equations from this 16 to 18 or 19. You remember this equation number 19, and it will serve your purpose. As you know the expression for the flat band voltage, so in terms of flat band voltage, you can remember the expression for the threshold voltage. It will be easier. So equation number 19 is convenient for you to calculate the flat band voltage of the MOSFET. So VTH equal to Q dash SD maximum by COX plus flat band voltage plus twice phi FP. So you know the how to calculate phi FP. You know how to calculate phi VFB, and Q dash SD is also known because you know Q dash SD is equal to QNA into XDT. So now you can also notice equation number 19. Uh, Sometimes you may be asked the question that what are the factors which determine or which influence the threshold voltage of MOSFET. Then what would be your answer? What are the factors which control the threshold voltage of a MOS device? This Tuhin Sarkar. Have you followed my question? What is your answer? You tell me in terms of material parameters. Means geometrical and material parameters. Material and geometrical parameters. What are those parameters? No, no, no. In COX is a complex thing. Means it depends on the geometry as well as material parameters. Material parameters means it depends on the metal semiconductor work function difference, isn't it? It depends on the Na. Na means it is the substrate doping concentration. And geometry actually influences the geometrical parameters influence the value of COX, because material parameter is also involved because of this epsilon. But epsilon A by D. A is unity, but D is there, means the oxide thickness. Thickness is the geometrical parameter, you can say. So within this expression, you need to think carefully. What are the parameters, mean geometrical and material parameters, which influence the value of threshold voltage. So if you were asked, how can you set or adjust the threshold voltage of MOSFET? How can you do it? Is it so simple? Because in any technology node, the oxide, this thickness is fixed. You cannot do it. There is some specifications where you need to keep the oxide thickness fixed. You are not allowed to vary it for a particular technology node. For a given technology node, you are not allowed to vary the thickness of the oxide. Yes, yes, yes. So it is a clever technique to vary the metal semiconductor work function, because you can choose different metals. Metals are available with varying work functions. And some composite materials are there where you can vary work function, that is tan tin, this combination. So by varying the nitrogen content, you can also vary the work function value over a certain range. So most simple and clever technique to vary the threshold voltage or to adjust the threshold voltage of the device is to actually change or manipulate the work function of the metal. So next we can see this problem. So consider an N plus polysilicon gate and a p-type substrate doped to Na equal to 3 into 10 to the power 16 per cc. Assume Q dash SS equal to 10 to the power 11 per unit per square centimeter, and phi ms is given minus 1.13 volt. Determine the oxide thickness such that VTS equal to 0.65 volt. So first you need to calculate the value of phi FP. Phi FP equal to VT ln Na by Ni. So it is equal to 0.0259 ln 3 into 10 to the power 16 divided by 1.5 into 10 to the power 10. So that is equal to 0.376 volt. So x dt, it is a known formula. So it is equal to 4 epsilon s phi fp. This E means Q actually. Q into Na whole to the power half. So it turns out to be 0.18 micrometer. Micrometer means 10 to the power minus 6 meter or 10 to the power minus 4 centimeter. So Q dash SD maximum, it is equal to Q into Na into x dt. So it is equal to 1.6 into 10 to the power minus 19 coulomb. Na is the actually 3 into 10 to the power 16, and x dt is the 0.18 into 10 to the power minus 4 centimeter. So the charge, depletion charge per unit area, it is equal to 8.64 into 10 to the power minus 8 coulomb per centimeter square. So now the oxide thickness can be determined from this threshold voltage. Threshold voltage is given. In this equation only unknown is T oxide. So if you substitute all the values, then this oxide thickness will come out to be 504 angstrom. That means 50.4 nanometer. So it is a very thick, usually such a thick oxide layer is not used nowadays. So it is for this problem, it turns out to be Tox equal to 50 nanometer. So is it clear? I shall give you this notes, so you need not worry or copy this one. Everybody will get it. So if you have any question, you can ask me. Otherwise, I will close this notes and I'll open another.
Yes, sir, clear.
Okay. Mhm. So today I shall discuss the drain current model. In my earlier lecture, I also discussed is mainly qualitatively. Today I shall discuss this quantitatively, the drain current model. First, you uh, observe this schematic diagram of the cross-sectional diagram of a MOSFET, and the coordinate system is more important. So here we have used this N-channel MOSFET. Therefore, the channel is P-type silicon, and source is doped with N plus, means heavily doped with donors, and so does the drain. And there is an oxide layer which separates gate from the channel region, and the gate metal is there where we can apply some gate voltage, VG. So if VG is above threshold voltage, there will be a creation of the inversion layer at the interface, and on application of a positive drain voltage, there will be flow of electric current from drain to source through the channel. And we consider this is the x-axis in the vertically downward direction, and y-axis along the interface from source to drain, and origin is the source channel junction. This is O. So this is the coordinate system. So now, if we assume that phi xy, it is the intrinsic potential at point xy, and we assume Vy, that is the electron quasi-Fermi potential at a point y along the channel with respect to the Fermi potential of the N plus source. Suppose N plus source is grounded, therefore here the potential is 0, and at the drain terminal it is VDS. And in between, we can assume there is a linear increase of this potential Vy from source to drain region. So therefore, we can express it simply by Vy equal to y by L into VDS. It is not written in this notes. You can write it down. So Vy, we can approximate it Vy, that is equal to y by L into VDS. So when y equal to 0, Vy equal to 0. When y equal to L, Vy equal to VDS, or the drain potential. And you know that this channel potential Vy acts as the reverse bias to the channel substrate that I already explained earlier. This Vy means the potential at the interface. What is Vy? Vy is always positive because at the drain terminal we apply some positive voltage with respect to source so that it can attract electrons from the channel. So when inversion layer is formed, means at the interface you will find a sheet of electrons. And if you go down within the substrate, you will find a p-type material. This is the p-type substrate, p-type silicon. So there is a N, means a sheet of electrons, means N-type semiconductor, and underneath this there is a p-type semiconductor. And Vy is applied at the interface. Vy is positive. So positive voltage is applied to the N diode, means this channel to substrate diode. Therefore, it is reverse biased. So Vy actually acts as the reverse bias to the channel to substrate diode. So therefore, uh, while calculating the electron concentration at any point xy, we can write it nxy. It is the electron concentration at the point xy that is given by ni square by na e to the power q electrostatic potential minus reverse bias V divided by kT. So this equation is very important, equation number 16. So if you have any doubt, you can ask me. So the condition for surface inversion becomes this phi 0 y. So phi 0 means electrostatic potential. It is not constant throughout the channel. So it is equal to Vy plus twice phi b. Phi b and phi fp both are same. So which is a function of y, because Vy varies along the channel. That is why phi 0 y, this actually potential also varies with y. So what is the value of the maximum depletion layer width? It is xd. It is equal to root over twice epsilon I into Vy plus twice phi fb divided by q na. So here you see that in the expression for the maximum depletion width, there is Vy. So that is why you will find that at the drain side, the depletion layer width is higher as compared to that at the source side, because of the presence of Vy. Because Vy is equal to Vdd at the drain end, and Vy equal to 0 at the source end. So therefore, the depletion width becomes more wider at the drain side as compared to that on the source side. So now we apply gradual channel approximation, which I already discussed. So what is that gradual channel approximation? It is actually this approximation assumes that the variation of electric field along the channel is much less than the corresponding variation in the perpendicular direction of the channel. Means in the vertical direction, the variation of electric field is much higher as compared to that along the horizontal direction. So that is why if we consider this gradual channel approximation, it actually converts the 2D Poisson's equation to one-dimensional Poisson's equation. We take only variation of electric field in the x direction. So uh, and there is no or negligible variation of electric field along the y direction. That's why we take the Poisson's equation with reference to x only, x coordinate only. So this is actually is true if we assume this gradual channel approximation. How further we can assume that both the whole current and the generation recombination current are negligible. So therefore, we assume that the current continuity equation can be applied to electron current in the y direction only. So we are neglecting whole current. We are neglecting any current due to generation and recombination of carriers. And therefore, we consider only the electron current. That is why we consider the current density equation due to electrons only in the y direction. So electron current density at a point xy, that is given by Jnxy, that is equal to minus q. Minus q is the electronic charge, mu n is the electron mobility, nxy is the electron concentration, and this is dvy dy. This is equation number 19. It is the electron current density at a point xy. Now, you must note that the bulk mobility of electrons is much greater as compared to the channel mobility. Actually, the MOSFET mobility or channel mobility is much lower as compared to the bulk mobility due to the presence of the additional scattering mechanism, that is the interface scattering. So due to this, in the bulk, there is no interface scattering. That's why the mobility of carriers is much more as compared to that in the interface. So if you take into account this surface scattering or interface scattering, there will be a low value of electron mobility. So in order to get the total current, current means the current density into area of cross section. So you have to multiply this equation 19 with actually W is the width of the channel, and you have to integrate over X. Xi is the thickness of the inversion layer. So you must integrate from 0 at the interface, and Xi is the width of the inversion layer. So this integration is carried out over this variable X. So therefore you can take dv dy out of this integration. Okay. And another important thing is that this under this bias condition, you can take mobility of electrons with replace this mobility of electrons with some effective mobility, mu effective, so that you can take this mu n out of this integration. And Qi, it is the inversion charge per unit gate area, that is equal to Qi function of y, that is minus q integration from 0 to xi in xy dx. So this equation 20, and that becomes equal to IDS. It is the drain to source current. It is a function of y, that is equal to minus mu effective W dv dy into Qi y. So you can change this variable, then you can uh, replace y with v. So now multiply both sides with dy, and again carry out integration. So on the left hand side, you have to integrate over y. So from y varies from 0 at the source end and L at the drain end. And on the right hand side, v means it is at the source end it is 0, at the drain end it is vds. So therefore here the current IDS, it will remain same throughout all values of y, because there is no diversion of this current. So if we apply this KCL, Kirchhoff's current law, it will be same. So therefore IDS into L on the left hand side. So just take L on the right hand side, therefore it appears on the denominator. So mu effective into W divided by L, say integration from 0 to VDS minus Qi V dV. So now use this equation number 16, which I showed you earlier, and do some substitution, and you can get the value of Qi V. It is a function of V. Inversion charge density, it is a function of V, and you will get this integration. So from phi s surface potential to phi v. Phi v means phi fp. So n phi v dx d phi d phi. So d phi will cancel out. And if you put this value of this electric field E is a function of phi and v. It is equal to minus d phi dx. So from equation 26, you can get this equation. From equation this 24, you substitute the value of Qi V, then you can arrive at this important equation 27, that is IDS, drain to source current, that is equal to Q mu effective W by L. W is the width of the channel, L is the length of the channel, integration 0 to VDS, then again this integration is over V dV, and this inside integration is over phi d phi. So lower value here is this phi b, and upper one is the phi s. So it is a double integral. This double integral is known as the Power-Shah double integral to determine the drain current. So it appears in the examination many times. Derive an expression for the drain current using this Power-Shah integral, or this derivation is very important, and you go through this derivation. I'll give you these notes, and You need not remember all these steps, but the important thing you must remember. So if you have any question regarding this drain current model using this Power-Shah double integral, you can ask me. There are some limitations I'll discuss you now. This Indrajit, is it clear?
Yes, sir, clear.
Okay, so can you tell me what could be the limitations of this integration? Means limitations of this method of finding the drain current? Shreyashi, can you tell us something regarding limitations of this method? Sudeep, or Bobita? Actually, limitations are hidden in the assumptions, within the assumptions. What assumptions we have made? We have made the gradual channel approximation, where we have converted the uh, actually second order this 2D Poisson's equation to 1D. It is not always true. That means if we consider short channel MOSFETs, so where the gradual channel approximation does not hold good. So this is one limitations. Then we have neglected the current due to holes. We have neglected the generation recombination currents. So this is true for silicon, but if we consider any other semiconductor where the generation recombination of carriers actually are much higher, then you need to take into account those effects as well. So these are the limitations and which are not included in this model. But in order to get a better insight how current flows in a MOSFET, it is a very good actually model developed by Pao and Shah. Now I come to, this is the expression for the gate voltage. Gate voltage is flat band voltage plus surface potential minus Qs by COX. Qs is the charge per unit area at the silicon surface, and therefore Qs equal to it is given by this equation number 29 root over twice epsilon silicon and then Kt Na within the bracket Q phi s by Kt plus Na square by Na square e to the power Q phi s minus V by Kt whole to the power half. So if you just actually rearrange this equation and make this substitution, you can get the expression for the uh, gate voltage in terms of this phi s surface potential. So it is an implicit equation for this phi s. So this equation number 30 and equation number this 27. These two equations are coupled together. Here you see the expression of phi s. You carefully observe. So these are known. Vg is known, Vfb is known, but phi s you have to calculate it. Again, phi s is here in the within this limit. So therefore, these two equations means 27 and 30. These two equations are coupled together, and you have to solve for this equation numerically. Sometimes you need to take into account the iteration technique as well. But here you see some exponential term is there on the second term here, e to the power q phi s minus v by kt. So therefore, uh, although it looks a little bit complicated, but it is you can solve it by this MATLAB programming also. So are you conversant with the MATLAB code? Indrajit, are you conversant with the writing of MATLAB code?
Sir, not so much very much, sir. Basic,
Okay.
sir. No.
But you are learning now, there is a course on mathematics in this semester.
No, sir. I'm sir from VLSI design, sir. It is for
Oh,
RP.
it is in the VLSI design. Okay.
Yes, sir.
But what about VLSI students? Have you learned this MATLAB code, how to solve these coupled equations?
No, sir.
Not
No,
yet.
Not yet.
not yet.
Okay. So today I'll stop. If you have any question, you can ask me. So in my earlier lecture, this derivation was not there. So now I think it is clear. If you have any question, you can ask me. Okay, thank you. So you will send your attendance to my email, both RP and VLSI design, this CRs.
স্যার আগের দিনেরটা পেয়েছিলেন?
আগের দিন কোন মেলে পাঠিয়েছিলে? রেডি মেলে পাঠাবে আমার। রেডি
রেডি
মেল,
মেলে
হ্যাঁ
পাঠিয়েছি,
হ্যাঁ হ্যাঁ।
রেডি মেলে পাঠিয়েছি আমি।
এ বিশ্বাস, হ্যাঁ একজন পাঠিয়েছিলে, এ বিশ্বাস 5@redipmail.com, ওইটাতে পাঠাবে। আচ্ছা, আমি আগের নোটটা দিয়ে দেবো, এটা পড়ানোর পর তাহলে দেবো। এটা আর কিছু আছে, নেক্সট পড়িয়ে তারপরে দিয়ে দেবো, আর আগেরটা দিয়ে দেবো আজকে। ওকে।
ওকে স্যার, থ্যাংক ইউ।